Hello my dear students, I warmly welcome you to CS Digital Classes. In this lecture, we are going to discuss about Little Fermat's theorem, one of the important theorem for the short answer purpose. And in the long answer, this question will come in the option wise, option A or option B. Okay. So first of all, see the theorem statement. Okay. State and prove Fermat's Little theorem. Okay. Don't worry if there is any big theorem. So this is the only one theorem. Okay. Fermat was the mathematician name. Okay, so state and prove Fermat's Little theorem, and the statement is for every integer small a and every prime number p, a power p modulo p is equal to a into modulo p. Okay, I will explain what is the meaning of that. Or else a power p congruence. Okay, congruence modulo p. Here you have two symbols. Okay, the first symbol is equal, and the second symbol is congruence. What is the difference between equal and congruences? Okay, so equal represents the two sides of equal. You can, whenever you represent equal, the left hand side and the right hand side both are equal. Whenever you write the congruences means this one. Okay, whenever you write this congruences, you have to apply the divisibility condition. Okay, but in that case also left hand side is equal to right hand side, but the right hand side value denotes the remainder. Okay, here whenever you write a power p congruence a modulo p, a power p congruence a modulo p, it gives that original definition if and only if this p prime number divides a power p this minus a. Okay, this a power p and minus a, this is the original definition. Okay, you will study about this congruences topic in higher studies, that is in MSc mathematics. In number theory you will get that concept. Up to now you have to by heart that concept. Okay, so because it is a big concept to introduce you, so a power p congruence a modulo p is nothing but p divides that the prime number what the given modulo value p is there, that p divides the LHS subtraction of LHS value and the RHS value. You have to remember that. Okay, so the modulo value, whatever you have that modulo value p, that p divides the subtraction value of LHS and RHS values, the subtraction value of LHS and RHS. That is the difference between equal symbol and congruences symbol. So we are entering into the proof of this theorem. Given small a is an integer, that is a belongs to z, and from the statement only we have p is a prime number. Okay, so now to prove this theorem we are using the one of the important topic in mathematics, so that is division algorithm. Already this division algorithm we have used in the several theorems, okay, in the previous lectures. So by division algorithm there exist any two integers. Okay, the first one is small m and the second one is r, such that you can write a is equal to p into m plus r. Okay, p into m plus r with remainder. Small r is the remainder. Remainder is always lies in between 0 less than or equal to small r less than p, where p is the quotient. Okay, so you can I will give that diagrammatic representation for that. Whenever you write a is equal to pm plus r, a is equal to pm plus r, in the diagrammatic format a is the dividend. Okay, so m is the divisor, you have to divide with a. Okay, so p is the quotient, you will get some b here. Okay, m into p is equal to b. After taking the subtraction you will get one remainder small r. Okay, so this is the division algorithm. While you are doing, for example, if you take 10, okay, if you divide that 10 with 5, 5 2s are 10, you will get the remainder 0. Now this dividend 10, you can write 5 into 2, 5 into 2 plus remainder value 0. Like that only, in the same manner, I am writing this dividend small a is equal to, okay, m into p or p into m plus r, where the remainder value starting with 0, 0 less than or equal to small r less than p. Okay, remainder value always lies in between 0 to the quotient value p. Okay, so that is from the division algorithm we can write that value. So that is taken as equation number 1, where p is a quotient and r is the remainder. Next you can see here equation 1 can be expressed in terms of congruences. Whenever you write equation 1 a equal to pm plus r by division algorithm, the division algorithm we can express in the congruences format. That means a congruence smaller modulo p. A congruent smaller modulo p. That means whenever if you divide small a by p, r is the remainder. Whenever you divide small a by p, r is the remainder. That is the meaning of equation number 2. You can write in the congruence format by using that division algorithm. Here small m is the coefficient, we are ignoring that value. Now to prove this theorem, it is sufficient to prove the theorem a power p congruence to a modulo p. To prove the given theorem, so we have to prove that a power p congruence to a modulo p. If you prove this condition, that gives the total proof of the theorem. To get that condition, here we are going to through two cases. Okay, the case 1 depending upon the remainder values only. In case 1, we are taking the remainder r is equal to 0. Then in case 2, in remainder r not is equal to 0. If you take r is equal to 0, what will happen? If you take r not is equal to 0, then what will happen? We have to discuss. So now see, in case 1, if you take remainder r is equal to 0, okay, substitute r is equal to 0 in equation number 2, then you will get a congruence 0 modulo p. Whenever you write a congruence 0 modulo p, 0 into something in RHS, again you will get 0. So a equal to 0. A equal to 0, if you substitute in this equation, or else you can give this equation as star. Okay, if you substitute a is equal to 0 in equation star, then left hand side will become 0. Okay, this total part will become 0 and the right hand side part will become 0. So therefore both sides of equation star will become 0. So therefore whenever you take remainder value r is equal to 0, the condition, the required proof is trivial. Okay, so no need to prove the given condition whenever r is equal to 0. The problem will stop there only. Okay, but we are not getting the required condition. To get the required condition, we are going to the second case, that is r not is equal to 0. Sometimes if you get remainder not is equal to 0, okay, then if you get remainder not is equal to 0, then what is that meaning? You will get greater than 0. What are the greater than 0 values? 1, 2, 3 up to so on. What are the possibilities for the remainder? That remainder is always lies between 0 less than or equal to small r less than p. Less than p means the last value of the last possible value of the remainder is p minus 1. Okay, from 0. First of all, if you start with 0, in 0 we got the trivial case. Okay, if you go to the not equal to 0, okay, then next value is 1. 1 to p minus 1. Okay, if you observe carefully, this set is already we discussed in the previous lectures. That is the set of positive integers not exceeding the given number p, and it is a group of positive integer under multiplication modulo. Okay, then that group you can write with as u of p. Small r belongs to u of p, where small r is the remainder. Remainder is the any one of the value, 1 కావచ్చు, 2 కావచ్చు, 3 కావచ్చు, up to so on ప్రైమ్ నెంబర్ ఎంతైతే అంత. ప్రైమ్ నెంబర్ 5 అయింది అనుకోండి, 5 మైనస్ 1 4 వరకు ఉండొచ్చు. లేదంటే ప్రైమ్ నెంబర్ మీరు 7 తీసుకున్నారు అనుకోండి, మాడ్యులో 7 7 మైనస్ 1 6 వరకు రావచ్చు, 6 కూడా కావచ్చు. సో దేర్ ఫోర్ ఆర్ బిలాంగ్స్ టు యూ ఆఫ్ పి బేస్డ్ ఆన్ ద ప్రైమ్ నెంబర్ 1 2 3 up to so on p minus 1 ఈజ్ ఏ ఫైనైట్ గ్రూప్ ఆఫ్ పాజిటివ్ ఇంటీజర్స్ అండర్ మల్టిప్లికేషన్ మాడ్యులో p. ఓకే, సో ఎప్పుడైతే రిమైండర్ నాట్ ఈక్వల్ టు 0 అవుతుందో, నాట్ ఈక్వల్ టు 0 అంటే ఖచ్చితంగా అది ఈక్వల్ టు 1 నుంచి p మైనస్ 1 వరకు ఈ వాల్యూస్ మధ్యలో ఏదో ఒక వాల్యూ రావాలి. ఆ వాల్యూ మనకి ఏంటంటే ఈ సెట్. ఆ సెట్ ని నేను ఏమని తీసుకుంటున్నా అంటే u ఆఫ్ p. ఇట్ ఈస్ ఎ సెట్ ఆఫ్ పాజిటివ్ ఇంటీజర్ అండర్ అడిషన్ మాడ్యులో p. ఒకవేళ z ఆఫ్ p రాసాను అనుకోండి, సెట్ ఆఫ్ పాజిటివ్ ఇంటీజర్ అండర్ అడిషన్ మాడ్యులో. ఇదేమంటే మల్టిప్లికేషన్ మాడ్యులో. ఓకే, సో దేర్ఫోర్ ద ఆర్డర్ ఆఫ్ u ఆఫ్ p. ఇప్పుడు మీరు ఆ u ఆఫ్ p లో ఉన్న ఎలిమెంట్స్ ని కౌంట్ చేస్తే మీకు 1 నుంచి p minus 1 వరకు p minus 1 ఎలిమెంట్స్ ఉంటాయి. సో దేర్ఫోర్ mod u ఆఫ్ p is equal to p minus 1. దట్ ఈస్ టేకెన్ యాజ్ ఈక్వేషన్ డబుల్ స్టార్. ఆల్రెడీ మనకి స్టార్ ఉంది, డబుల్ స్టార్. ఓకే, ఈక్వేషన్ డబుల్ స్టార్ బై నాన్ కరోలరీ. ఓకే, అప్ టు ఆర్డర్ ఆఫ్ ద u ఆఫ్ p is equal to p minus 1 is okay. Okay, now to get the required condition, what we have to get? A power p congruence to a modulo p. We have to get this condition. To get this condition, now I am taking one property, that is by noun corollary, or you can write by noun theorem. If capital G is any finite group with A belongs to capital G, then order of that element is equal to order of the group. Okay, order of the element is equal to order of the group. A power mod e mod g is equal to small e. ఇక్కడ mod g is the order of the group g. Order of the group g నే order of the element అయితే. Okay, so that is the condition we are using here to solve this theorem. Okay, this total part we are using for the proof of this theorem only. Okay, this is also one of the very important problem. Okay, this condition have came in the previous examination 2022 June July for the short answer purpose. Okay, so now by using that condition, okay, by applying equation number 3 for the present scenario, for small r belongs to u of p, you get r power u of p mod u of p is equal to small e. ఇక్కడ small e అంటే with respect to multiplication కదా. With respect to multiplication, identity value is 1. Okay, so therefore, in place of a, we have small r. In place of g, we have u of p. Okay, so don't get confused. Okay, so r power mod u of p is equal to 1. Now, to get the congruence condition, I am taking modulo p on RHS. So therefore, r power, what is the mod u of p from equation double star? You can write r power p minus 1. Okay, mod u of p is equal to p minus 1 congruence 1 modulo p. మీరు సింప్లిఫై చేసుకుంటే r power p into r power minus 1 congruence to 1 modulo p. So r power minus 1, in next step it goes to denominator r power p by r congruence to 1 modulo p. Next ఈ small r ని denominator లో ఉన్న r ని if you send to RHS side, r power p congruence to r modulo p, that is taken as equation number 4. Okay, so here you can take a small breath. Why? Because it is in the form of the required condition. Now our aim is by replacing small r with small a. So therefore, by replacing small r with small a in equation number 4, you will get the required condition, that is a power p is equal to small a modulo p. Why? Because here small a is an element, small r is also element. Both are the elements, but small r is the remainder. Whatever it may be, at the end of the theorem, that is element only. So therefore, a power p congruence a modulo p. If you write in terms of congruence, you have to write in this format. Or else, if you write in terms of equality, a power p modulo p is equal to a power 1 modulo p. Okay, so therefore, for any integer small a, you can write a power p congruence a modulo p. This is the total explanation of the Fermat's Little Theorem. I hope you understood this theorem very well. So ఈ theorem లో ఏం లేదు, సింపుల్ గా రిమైండర్ మీద బేస్ చేసుకుంటున్నాం. రిమైండర్ r is equal to 0 తీసుకుంటే మనకి LHS 0 RHS 0 ఈక్వేషన్ స్టార్ లో, రిమైండర్ r not is equal to 0 తీసుకుంటే మనకు ఒక నౌన్ థియరం ని యూజ్ చేస్తున్నాం. ఆర్డర్ ఆఫ్ ఎన్ ఎలిమెంట్ is equal to ఆర్డర్ ఆఫ్ ఏ గ్రూప్. ఆ కండిషన్ యూజ్ చేసుకొని ఇక్కడ మనకు వచ్చిన ఆర్డర్ ఆఫ్ ఏ గ్రూప్ ఏంటి, మాడ్యులో p, ఆ u of p వచ్చింది కదా, అదే ఇక్కడ మనకు గ్రూప్ అవుతుంది. దాని ఆర్డర్ ని యూజ్ చేసుకొని ఏ ప్లేస్ లో స్మాల్ r ని సబ్స్టిట్యూట్ చేసుకొని సింప్లిఫై చేసుకుంటే you will get the required condition a power p modulo a power p congruence a modulo p by replacing small a by r. So therefore, this is the little Fermat's theorem. I hope you understood this theorem very well. In the next lecture, we are coming with another new concept. Okay, so make a perfect practice, prepare well. This is K. Viresh signing from CR Digital Classes. So until bye, thank you.